Okay, here we go. Here's part two of set 88, the lesson on exponential growth as it relates to differential equations. So, uh, yesterday we talked about differential equations being any equation with either a derivative or dy, dt, differentials in it. Usually we will solve differential equations, which doesn't mean you get an answer like x equals 2, but more like when you solve a differential equation, you're going back to the original yx or whatnot equation, right? So by way of introduction, let's consider back to pre-algebra. Remember when you did exponential, well, not exponential growth, but interest problems in pre-algebra. We started with simple interest. So imagine Joe starts with $10 and earns simple interest. That means he gets 10% every year. So at the end of year one, he gets $1, ends with $11, but the second year he still only earns 10% interest on the same original amount only, not the new amount. So he continues to go by a year each, $1 each year. So that is the change. Change is 1. Change is 1. If you were to look at that graphically, then the amount is changing by the same amount every time, and that is linear growth. If you were to look at this in a differential equation way, you would say the rate of change in the amount is constantly 1. Always $1 per year. Which, if we integrated, then we could say dA is 1 dt. Integrate both sides. A is 1t plus c. And then we could probably use the initial condition at time 0. The amount is $10 to get a final amount equation, 1t plus $10. Now, all that's great, but linear growth isn't very interesting. Actually, it's super important, but it's not very interesting. So, let's look at what's more common, which is exponential growth, or in this case, compound interest. Now, if it's continuously compounded every second, then you see E. But for this purpose, you're going to do compounded once per year. That means the first year will be the same. You'll still end with 11 because you're earning 10% on $10 the first year, just like in simple. But in the year 2, now you're earning interest on the new amount, interest on interest, and the original principal. So you're going to start to see this change there. The amount went up by 1.1, and in year 2, did I do that right? Nope. $1.21. Sorry. You're looking more like change of $1.21. When that's the case, the amount is growing at a new greater amount every time, you start to get a curve. And let's talk about today then. In this case, I could relate the rate of change to time, I guess, because it does depend on time. You know, the later the year, the more interest you can be making. But really the idea is that the rate of change grows or ties to the amount in the account. You're getting 10% of the amount in interest, or 110% growth factor every year. So that's pretty uncommon that the rate of change relates to the amount itself. That's like y, y's growth rate, depending on what y is rather than x. That does sometimes happen, and especially in differential equations. It's pretty important. So it's worth investigating. But for now, understand that that's to be noticed. Let's move on then. If we take this equation, that the amount grows at a rate proportional to the amount, and work our calculus magic on it, we could separate the variables and integrate, and we would get something like natural log of the absolute value of A equals KT plus C. Now, for this case, let's assume that the amount is positive. So I'm going to dump the absolute value. Because it's positive, the absolute value would be on this. So that means the natural log of A equals kt plus c. I'm also going to infer a subtle initial condition. There's nothing specifically given, but at time 0, the amount at time is equal to the initial amount. Now, if I put that in, and I get natural log of A initial equals 0 plus c. So c represents the log of the initial amount. Now, if I go back to my equation with that c in, natural log of A initial, natural log of A at time equals kt plus log of A initial. Let's continue up here. Now let's solve for A. If I exponentiate A equals e to the, when you exponentiate, it has to be a whole side, not a term here and a term there. So it's e to the whole side. Now that's nice, but it can be changed a little bit. By exponent rules, I know basically that if you have a sum in the exponent, it comes from two things with the same base multiplied. So using that idea to separate the two terms, e to the kt times e to the natural log of A initial. Now if I take that second term and simplify, e to the natural log of A initial is just A initial. That, then, that differential equation is what leads to the idea of exponential growth. When the amount grows at a rate proportional to the amount itself, bunny population doubles every 5 years. Well, it would depend on how many bunnies are there to begin with, or at that time. In that case, then, you get exponential growth. You really need to tie three ideas together, which I did for you. A verbal statement, the amount.
Hi, could you help Mr. Carlson in the math hall? He's got a light out.
The amount changes at a rate proportional to the amount. That's the same as the differential equation. The amount changes at a rate proportional to the amount. And with all the separation of variables we just showed, that leads to the exponential growth or decay equation, depending on if k is positive or negative. All right. So you need to recognize this term when you get to some problems. For example, when I say bacteria in a certain culture increase at a rate proportional to the amount present, I understand that the bacteria, that right away screams pre-calc exponential growth problem, but I want you to focus on is this part. Increase at a rate proportional to the amount present. That's calculus code for dA dt is constant times the number present. All right? That said, I don't expect you to start back at that differential equation. You can just hopefully say, oh, so that means I'm dealing with this idea. If it's the case that the number doubles every 4 hours, then I could say that 2 times the initial amount is what I get after a time of 4 hours. If I then divide A naught over log to get rid of the exponential and divide by 4, I could see that k is the natural log of 2 divided by 4. After that, then, I have everything I need to solve the other question. How many hours to triple? Well, that would mean I want to say when the amount after time is 3 times the original amount, how much time passes? I can put in my k, 3a times the initial, and solve 3 equals e to the natural log of 2 over 4t. Exponentiate log of 3 equals natural log of 2 over 4t. So t is 4 natural log 3 over natural log 2 hours. Okay, largely it's still a pre-calculus problem. You might think I've done that a million times, and you're right, you're right. We've done that before. Let's look at a different one, though. You haven't done this one before in pre-calculus, I'm sure. So here it says temperature changes according to the differential equation. dF dt equals Kf. K is a constant, T is time in minutes. Now that right there, my eyes light up when I see a differential equation where the amount grows at a rate proportional to the amount. So when those variables are the same, that's exponential growth. So I can avoid all the, I guess I should use F here. I can avoid all the separation of variables if I recognize that that differential equation is code for exponential growth and decay. Saves me all the calculus of trying to develop it, and instead I can now use this fact to find F initial. So that implies that F is 180 e to the kt. And then I can use this case to find K. 120 equals 180 e to the k after 16, whatever the units are, minutes. Divide 180 over and reduce, that's 2/3, natural log. Divide by 16, k must be natural log of 2/3 over 16. There are no units on that constant of proportionality. Don't worry about the units. Okay? At least I don't think there are units. All right, are you with me? I think that then is the meat of the lesson. I did, as a warm-up, do this free response. I'll let you try that, and I would suggest you try that first. So pause if you're going to try that, and then I will scroll down so you can grade how you would have done. So pause now and work. Okay, so let's see how you did. Here's the rubric for the first. First, understand that you do not have to integrate first to make a tangent line. You already are given a point. You can find the slope by the derivative, which you are given. So all you need to do is clearly find the slope by using the derivative. Write the equation of the tangent line. And then make sure you approximate the value of 1.2 by plugging 1.2 into your tangent line, and it is an approximation. That's 3 points, as you can see off to the side. The second part is solving the equations and solving for y. So you do have to separate the variables. One of these two steps would be sufficient for 1 point. After that, you need to integrate both sides. That's 2 points there, actually 3 points. One for the left side integration, one for the right side integration, and one for just putting the constant of integration down. The next point is for using the initial condition to find the c. And last, the hard part is doing all the mental gymnastics of solving for y. So check your answer, and hopefully got 6 out of 6. But the part I wanted to emphasize in class is that if you don't separate the variables and show that one of those two steps, you get nothing. They will not give you anything. So be careful, be careful, be careful. That first step is key. All right, here ended the lesson. I hope that was instructive, and thank you for watching. Have a lovely day.